Okay, just to quickly reiterate a couple of comments that I made on the major quiz. Okay, good news and bad news. Good news, everybody passed it. Everybody took it on time. Okay. I can't tell you how much of a shock that is from what I usually see in a pre-calculus class at this stage. Okay. So as I said, y'all are doing great. So that's the good news. Bad news is some of the passes were pretty low. Okay, good news is quite a few Bs. Bad news is no A's. Okay, now some of the Bs were close enough to A's. I just might curve the grade on this one just a little bit so I can at least say somebody made an A. I can't say who that will be because right now, well, I can say, yeah, I know one person that made an A if I curve it. Okay, now another thing on the grading I've done up to this point is pretty approximate because like I just got the tests that you took late last night, a little over an hour ago. Okay, so I had to take a pretty quick look at it. And all the grading is a pretty quick look. I want to go back and grade everything all at once so that I can make sure the grading is uniform. Because I graded it like in 3 stages. I got some a few days ago, got some yesterday, graded them last night, got some this morning. I'm not sure I was totally uniform in the way I graded. So that can be an advantage because I'm not going to lower anybody's grade when I do this. Okay. So if I've got to make adjustments, it's going to keep your grade the same or improve it. Okay, probably not by much because I'm pretty consistent. I know what I'm looking for, but did I take 2 points off for that or did I take 3 points? Okay, if I took 3 points off in yours and took 2 points off in somebody else's, well, you're getting an extra point. That sort of thing. Make sense? And I probably will curve the grades just slightly. They don't have to be curved much. I think the highest score I saw was 87. So I know that I'm going to curve things up consistent with raising that 87 to 90. Okay. And at the lower end of the scale, that means since we've got this kind of rubber band normalized scale that I'm not really going to explain right now, the lower your grade, the more points that'll have. Okay, so if I raise something that's almost an A by 3 points, that means I might raise somebody who just barely passed with a 60 of the normalized score. That may be fine. Like half a letter at the low end of the scale. Okay. Okay. There are things that we need to understand, which is number one, that everybody in here, and I'm repeating myself because I said this earlier, but everybody in here, it seems to come in really well prepared, at least pretty well prepared, usually really well prepared for the daily quizzes. I see evidence that maybe stuff didn't stick with you from earlier, or you didn't really get it earlier, but mainly that maybe you didn't review enough. Now with all the pressure, time pressure and everything, maybe cut the review a little short so you keep up with the assignments. It's going to be okay. You're going to take a midterm. The midterm's going to be a little tougher, and I'm going to grade it a little tougher. Because now you've had a sample, you know what to look out for. And I'll probably extend the midterm past next Wednesday. Everybody passed. I don't see any need that anybody should have to drop the course unless you made a low pass and you really have to have an A. Okay. And even the people that made the low passes, they've shown evidence they can do A work if you have the time to do it. Okay. So don't be discouraged if you have a low pass or a mediocre pass. Okay. The deal is going to be, I'll probably extend the major quiz all the way through the week from Monday. And not the major quiz, I'm sorry, the midterm. You got to have a word for the major quiz. It doesn't start with M, so I don't keep getting confused. Midterm has to be midterm. Okay. but it'll give you a chance to improve your review, improve your skills. We'll probably add a couple of topics to the major quiz. It'll probably cover everything we've done up through rational functions. Okay. Maybe even a little bit of graphic exponential functions, which might be optional, maybe not. I haven't decided yet. I'll let you know next week. Okay. Yeah, a lot of it's pretty easy, so that might be your advantage to do it. What else do you need to know? Well, let me see if you've got any questions at this point. Want me to clarify anything that I've said? Okay, one thing I didn't say is that your score on the major quiz won't be less than the score you make on your midterm. So even if you made, you know, like the 20% you made, no. Even if you made a lower score than you want, even if you made a low pass, okay, you can raise that to an A if you ace the major quiz. Okay. So that's as fair as I can be. Really, I want to see what you do. I don't know if I mean midterm or major quiz. Just, you know, we stated clearly, your score on the major quiz will not be less than your score on the midterm. I got it right that time, didn't I? Okay, if I'm not getting it right, just give me a thumbs down or something. I'll try to fix it. Okay, hang on a second. Okay, I'm just going to go over again real quickly, more quickly, what we did in the support course. In the support course, we do things before we do them in here. Seems to work pretty well. So I asked 3 questions here. Okay, first of all, graph f of x equals 2 to the x plus 3 plus 2. Okay. Now, it's a little challenging because there's something a little different about the way this function is written than the way you're used to saying. Okay. If it was x plus 3 squared plus 2, you know that you shifted 3 units to the left and up 2. Shift the x squared function. Three to the left and up 2. And I didn't do this now in the last hour. So there we have an example of what happened. Because why do you do this? Because you've replaced x by x plus 3. It's the x squared function. Okay. You have to replace x by x plus 3 to get this, which shifts you 3 units to the left. Then you add 2, which shifts you 2 units up. Okay, well, that's not really what we're doing here. So I'll put a little light x through it, okay? But just to give you the idea, because everybody's pretty good with transforming the x squared function, and most of the others. Okay, the exponential function looks a little weird because now x is in the, x is the exponent of your basic exponential function. So we start with a basic exponential function, 2 to the x. And then we do 2 to the x plus 3. Now, what did we just do? We replaced x by x plus 3. What does it do when you replace x by x plus 3? It moves the graph 3 units to the left. It moves every point 3 units to the left. You should understand why that is. We had early discussion. I can't do it now for sake of time. We had early discussions about why that moves the graph to the left. And it comes down to, in order to get the same value from this function that you get from this, x has to be 3 units bigger. Or, I mean, 3 units small, 3 units less. So I just said it wrong, but there it is. Okay, well, you might want to review the reasons that the graph shifts 3 units to the left instead of 3 units to the right, which is kind of the way it looks if you don't think about it. You don't remember the rule. Okay. And as I've always said, it's better to remember why the rule is because it's easy to forget the rule. If you just blindly apply the rule that you've memorized, well, that's okay. That'll get you by the test unless I'm asking you to explain it, which I might. And it's good. You know, it's good to be able to do that. Even better, understand why things shifts the way it does. Okay, we did a lot of discussion of that early in the course. Might be time to really kind of lock in why that is. Okay, anyhow. So, you know, we take the points of the 2 to the x graph. 2 to the x graph is in blue. These points are blue, so those points indicate the basic exponential function, the corrective points on the basic exponential function. And we shift all those points 3 units to the left. There are arrows shifting us 3 units to the left, and we end up with these points, which could be emphasized by this curve. And there's the graph of 2 to the x plus 3. So there's our y equals 2 to the x plus 3 function in yellow. If you're colorblind, well, it's this one. If you are colorblind, let me know what colors you have confusion on. Nobody has mentioned that, but I've got friends that can't see red. Okay. Okay, well, anyhow. Then what do we do? What do you have to do to 2 to the x plus 3 to get 2 to the x plus 3 plus 2? You got to add 2 to the y value, so you're going to raise it 2 units. There it is. Okay. So there's the picture. Now we had extensive discussion of that in the support class. Okay. So if you need extensive discussion of that, you know where to look. And here's all the explanation. The explanation is x replaced by x plus 3, so the horizontal shift is -3. It's a statement you need to understand in all the depth that you can, so you remember. And then y increases by 2, so the vertical shift is +2. Now, we have y equals 1,000 times 2 to the t. Okay, well, when I set up this graph, well, actually, okay. Let's see what we do. I didn't want to do 1,000 times 2 to the t without first doing 3 times 2 to the t. Something reasonable that you can see in the graph. Because if you go to 1,000 times 2 to the t, your basic exponential function looks flat. I'll explain that just a little bit. Again, explain more in the video from MD61. Okay. So 3 times 2 to the t. First thing you kind of want to look at is what's the range of this function? Well, the range, 2 to the t can't be negative, but it can be really small, right? No limit to how small it can be when you go into the negative values. And if you understand the calculations for the basic exponential function, you understand why that is. Okay. Everybody, it seems to understand those calculations. So you really, it's why I emphasize, show me the graph and show me the calculations. I wasn't real strict on the show me the calculations part on the major quiz, but that's just on the, yeah, it was a major quiz. That's the standard. That's a standard of documentation and explanation. Show me those calculations. Just don't write down what you think. Okay. Because sometimes it's wrong. Okay. The range of the basic functions from -2 to 2. Again, what I expect you to understand. Okay. We always graph these things -2 to 2 in this course. Then if you want to extend it, and often you do need to extend it, that's fine. But we at least graph it from -2 to 2 using the basic points. Well, if we go out to 2, this is 3 times 2 to the t, which is 3 times 2 squared, which is 12. So we set the graph up, it goes up to 12. And then we start putting the rest of the y scale in. The x scale is as it is, but we do a y scale that's going to make sense for this function so we don't run out of room. Okay, so we have 12 here, so A would be here, 4 would be here. It's not real, that's a little short, that might be a little long. But there it is. And then we could do a table. We could multiply 3 times 2 to the negative 2 and 3 times 2 to the negative 1. It's not the way we graph by transformations. We graph by transformations by starting with the basic function, when it's possible to do that. Really not possible on the 1,000 times 2 to the 2. Okay, so there's our basic function. And we multiply all the y values by 3, which means we triple every y value, which means that this y value becomes 3 times as great, meaning we move 3 times as far from the axis. That doesn't look like that moved 3 times as far. It looks like 2.5 because my 4 is a little high here. But if you do the graph properly, you can see what's going on. So like here, I drew 3 arrows. This arrow represents the y value when x equals 1. You don't even worry about what it is. I mean, you know what it is. It's 1. I mean, it's 2. Okay. I mean, triply, it's going to give you 6, but graphically, it's this far, and then it moves this far and this far again. It triples. Here's the y value of this point. It goes this far and this far again, it triples. So you triple it, and you do that visually before you even think about the numbers, and then you see if the numbers work out. And you don't make a table to graph this function by transformation. Okay. So there it is, and the explanation is y equals 3 times 2 to the triples all the y values of y equals 2 to the t. Shown that graphically. We've done that earlier in the semester for the exponential function, including others. And then we get the graph of y equals 3 times 2 to the t using transformations. Now, for 1,000 times 2 to the t, you can't use transformations. Why not? Because your range goes all the way up to 4,000. 2 to the second power is 4. Okay. And 4 times 1,000 is 4,000. So there's 4,000. Now, where is 4, which is the maximum y value you get for the basic function? Well, you subdivide 4,000, you get 2,000. Divide that in half, you get 1,000. Divide that in half, you get 500. Divide that in half, you get 250. Here's 125. Where's 4? It's so small on this scale that it looks like it's still on the x-axis, or the t-axis in this case. So every point looks like it's on the t-axis when you have this huge scale. So you can't really illustrate how you're raising it by a factor of 1,000. And even if you could, you wouldn't want to draw 1,000 of these little arrows for each point. No. Okay, so it's not practical to do that, but you understand in terms of what happened for smaller numbers, what is going to happen here. And of course, you know the values of the basic exponential function. 4, 2, 1, 1/2, 1/4. So you can multiply 1,000 by 4, you get 4,000, 1,000 by 2. Well, you can do all that. Okay. Well, it's not a property of the exponential function. It's really a central property. It's the idea of doubling time. And now this isn't in the what we talked about. We did talk about it in a way. I didn't use the term doubling time. Okay. But if t is interpreted as time, just look at this graph. What happens if you go from -2 to 2? Well, what happens if you go from t equals 1 to t equals 2? Your y value goes from 2 to 4. 2 ways to look at that. It increases by 2, but even more importantly, it doubles, right? Okay. What happens if you go from this point to this point? Y goes from 1 to 2, it doubles. Every time you move 1 unit to the right, Y doubles on any exponential function. Okay. Any exponential function with an asymptote at the x-axis. Same thing happens here. Okay, you go from 1 to 2, and the Y value doubles. You go from here to here, the Y value doubles. From here to here, the Y value doubles. Every time you move to the right 1 unit, the Y value doubles. So when you graph this thing, you don't really have to do calculations. To do it graphically, you take the biggest value, and then we move 1 unit to the left. We know it doubled to get from here to here, so what's it do to get from here to here? It comes half as great. Okay, every time you move 1 unit to the right, it doubles. Every time you move 1 unit to the left, it halves. So you have this, so you draw a point that's half as high. And then you move 1 unit to the left, you draw a point that's half as high. Move 1 unit to the left, half as high, 1 unit to the left, half as high. And you get this shape without having to calculate a darn thing, except maybe the coordinate of this point. Okay. Among other things, that means you can take a graph of the basic exponential. And not even label these points. Just put this point here, this point here, this point here, this point here, and get this point here. No, put this point here. Okay. Wait a minute. I lost track of what I was doing. This point should be a little higher. This point would go here. This point would go here. This point would go here. If I'm doing the basic exponential function like this, here's 4, and here's -2, and here's 2. Now we should have done this graph so many times. That's kind of automatic. And if it isn't, sure it is by the time you come in next time. Okay. Make sure you really understand these calculations, because it's really central to understanding the behavior of exponential functions. Okay, so here's a graph. Now the basic exponential function, this is 4, right? On this function, it's 4,000. So all I've got to do is label this 4,000, and label this -2, and label this 2, and I've got my graph of 1,000 times 2 to the t. There it is. I didn't have to calculate this. I didn't have to calculate this. I know what these are. This point is half as high as this. So if this is 4,000, this is 2,000, this is 1,000, this is 500, this is 150. Okay. So you can always graph an exponential function by drawing your basic exponential function without labeling it, and then putting the numbers on that match what your function gives you. We'll be doing that, so it's good for you to see that now. Okay. So anyhow, there's your graph of 1,000 times 2 to the t. It's a vertical stretch. Okay, this is a vertical stretch. I didn't write that down. Vertical stretch by factor 3. This is a vertical stretch by factor 1,000. Okay. And again, on this one, I could have just graphed these points as points on the x squared function, or the 2 to the x function. and then label this 12 instead of 4, and I'd have the graph. Again, we'll do that again with in other examples. Okay, what about this function? Okay, 3 times 2 to the negative x plus 1. What do we do? First of all, 2 to the x becomes 2 to the negative x if you replace every point by its reflection through the y-axis. Now, we haven't talked in class a lot about reflections, but you've done it in your homework. So you want to be sure you understand reflections, because when you reflect these points, it might be a little hard to see, but we've got a point here, point here, point here, or point here, and right here. There's our basic exponential function. And then what we did was we moved this point over to here, reflected it through the y-axis. This one's on the y-axis, so you don't have to reflect it. This one goes this way, and this one goes this way. And right here is our reflected graph. A little hard to see over here, but it becomes asymptotic to the positive x-axis, just like the basic function was asymptotic to the negative x-axis. And then we multiply that by 3. So here's our y equals 2 to the negative x. Don't confuse that with negative 2 to the x. It's totally different. It's a decreasing exponential function. Now, let me put in a blurb for increasing and decreasing exponential functions. An example of an exponential function that increases is the value of an investment at a given percent rate. So, for example, if you invest at 5%, turns out that about every 14 years, the value of your investment will double. Talk about that. You got this rule of 72 thing. But that's it. Okay. You know what your doubling time is. So this picture tells you what happens to that investment if you take the scale off of it. Okay. If you invest at about 7%, it doubles in a decade. So right here would be a picture of what your investment does if T is measured in decades. It's going to do this. Now, if you do the investment at T equals 0, it's going to go up like this. After 10 years, it'll be worth this. After 20 years, it'll be worth this. If you invest $3 at 7%, then it's initially worth $3. Right there's 4, right there's 3. After a decade, it will have doubled. It'll be worth $6. After another decade, it will have doubled. It'll be worth $12. Okay. After another 100 years, it'll be worth over $12,000. So if you live long enough, that $3 investment might grow. Okay, assuming the financial system stays stable for 100 years. It has for the last 100 years. Keep my fingers crossed for the next one. Okay. Well, nobody really plans to live in 100 years, but that's an example of how money grows. And that's a really important example for your personal finance. You want to understand that early, because that's when your investments have the biggest impact when you get old. Okay. Another example, and that I hope doesn't become too relevant to us, although even a limited nuclear war breaks out, it could. Radiation. Okay. Radiation tends to decrease exponentially. So if you've got this much radiation for this much radiation. Now it's going to fall off by an exponential curve with a negative. Okay, it's also relevant to, our governor, and I think it's good. Is talking about building modular nuclear reactors in this area. Okay, because people figured out nuclear reactors on submarines and aircraft carriers, and they can now be built cheaply enough and quickly enough that they can make a big impact on energy supply, reducing the amount of carbon dioxide you put in the atmosphere, which is probably a good thing. Okay, good thing to not put as much in the atmosphere, because there's strong evidence Greenland's going to melt, maybe Antarctica. Could be real inconvenient for people that live near the coast. Probably not good for everybody else either. If the science is correct on it, and it seems to be overall correct. They keep calling me, so I can verify to them that they're doing the right thing. So I keep telling them, yeah, that's pretty good. Keep okay. And I haven't found a good reason to discourage them at this point. Yeah, science is still science. So it's a learning curve, but that one's been going on for a while. Okay, so now what if we can exponentially decrease the amount of carbon dioxide in the atmosphere, assuming that's responsible for the majority of global warming? Yeah, that's a relevant thing to think about. Okay, and nuclear reactors don't put any carbon dioxide into the atmosphere. Okay, and this is a good area to build them in because solar power and wind power don't work real well. Not enough flat land, too much hilly, mountainous terrain. But the question comes up: what do you do with the nuclear waste? Because for nuclear waste, this curve is very, very slow, like on the order of tens of thousands of years, even tens of millions of years for some of the waste. So what do you do with it? Put it somewhere geologically stable and tell people not to live on top of it. That's what you do. And you hope people remember. If they don't, natural selection will take over. Okay. But you don't want to, we have good indication. The science tells us, the geology tells us that certain places stay stable for tens of millions and hundreds of millions of years. We can pretty well predict that they will. Can't ever be sure. Okay, well, there's things about exponential graphs, and then there's also the whole idea of horizontal compression you'll have to deal with. But there's also some discussion of important things, personal finance, decay of radioactive materials. And I'm using radioactive materials because it's kind of relevant to some of the news today. Recent news about the governor's plans for climate. And if those plans are followed through on, I think it's a positive move. Okay. But there's downside, radioactive decay related to that and so forth. There's also, they won't let me go out in public unless I take my medicine. But, I've settled down a lot. I think I'm okay. I think I'm safe to be around now. Well, seriously, if you're my age and you're not on some medication, there's something wrong with you. Of course, you are on medication, there's something wrong with you. I don't know how that works. Well, okay, I take my medicine in the morning and I stay sane through most of the day. Calm, not dangerous to anybody. Uh, I stay dangerous. I take a medication, take a blood pressure medication, okay? That blood pressure medication slowly gets removed from my system and it decays exponentially. So how does that affect my blood pressure? Well, one day I take it, it decays exponentially. Next day I take it, it hasn't decayed all the way, goes up a little higher. And then it decays exponentially. Okay, along the curve, just like what you get if you reverse your basic exponential function. With a half-life of maybe half a day, which means it drops to a quarter. Then it goes up. Now it's 1 1/4. It drops to a quarter of that, okay, which is 5/16, and then goes up, drops to a quarter, and all that stuff. Okay, that's how medications work. When you take your medication regularly, you keep increasing the maintenance dose, the maintenance in your bloodstream. Okay. So if you're on an antibiotic, you don't skip doses. If you understand exponential functions, you understand why you don't skip doses. Okay. You know, yesterday I got on the treadmill, went for an hour, climbing up 10% incline on the average. Okay. Not walking real fast, but you know, pretty standard pace. Okay. For somebody 100 years old, that's not too bad. Although there are people same age who have really exceptional genetics. That's a buddy I've talked to. Okay, ex-Marine, he was a fitness instructor. He was more fit than 99.8% of all Marines. Okay. He does a little better than I do. He's got better genetics. The genetics aren't bad, they're not exceptional, but they're okay. So he can do more than I can. Okay. I'm not competitive. I can't compete with him, so I shouldn't be competitive. Just root for him to continue to be healthy and make use of his good genetics. Okay, with my genetics, I find that on a 15% incline, my heart rate at the speed I walk will exponentially approach near disaster. Not really. I had a heart attack 9 years ago. Surgeon said, no limitations. If your body can do it, your heart can handle it. Now, when I get up that 15% incline, I've been going for a while. Doesn't seem that way, but I take his word for it, and I haven't keeled over yet. So I exponentially approach a certain heart rate with a certain half-life. At least that's the approximate model I can use. I don't really need that model. I know what it feels like. I know what my heart rate is. I know how high I want to keep my heart rate for how long. Okay. But it's very interesting to me. If I was training for the Olympics, they keep asking me to do that, but I keep saying, no, I don't have time. Okay. If I was training for the Olympics, if somebody was training for the Olympics, if I was a trainer training somebody for the Olympics, that would become very relevant. That kind of model would be very relevant. Okay. Because then what I do is I vary the incline. I go from 15% down to 10%. Actually, if I've been at 15% for a while, I want to go downhill for a while. But no, maybe I'll go from 15% to 5% just to keep my pulse rate going way up and then recovering, then going way up and recovering. At my age, high interval intensity training doesn't have the effect that it used to. So I don't do that much of it. Somebody who's in training, or somebody your age, and some of you are older than others, but compared to me, you're all kids. You young adults, even middle-aged people are young adults. And high-intensity interval training is relevant. And the exponential factors, the exponential model are very important. Okay, so I'm just telling you, exponential models come up in all kinds of places. And you can have this picture of an exponential model approaching this limit and then decreasing to approach this limit, increasing to approach this limit, decreasing to approach this limit. The curves all look like this. Sometimes they're more extended this way or compressed this way. Okay. Okay, so you're going to see in your first assignment some of the characteristics of exponential functions. Okay, and that's the assignment that's due on Monday. There'll be one due Wednesday where you get into the graphing. I started with the graphs because it's relevant to some of the things I saw on the midterm. It's relevant to some skills that everybody seems to have, but maybe hasn't applied properly to the exponential function. And also emphasize the need to understand the basic exponential function, because that's your picture of any exponential function. Now, sometimes we turn it upside down. We just put a negative sign out here, it turns upside down, right? Then we lift it up so that you can approach whatever heart rate you get here, okay? Or you can approach whatever drug concentration you're looking for. And then you lower the incline on the treadmill. Now you approach lower exponential function, okay? A higher one, then a lower one, if you keep changing. And that's just a fairly easy to understand example of how these curves can look. You get the picture of that. I'll even draw it. So let's say I go from an incline that gives me this heart rate, and an incline that gives me this heart rate. Okay, and I start down here. Well, I'll exponentially approach this. At some point, I decide that that's where I want to stop the training. So now I come down and approach this. Now, if that's enough recovery, I'll go up and approach this. You see an exponential curve here that have an asymptote here. Does that make sense? You see an exponential curve here that has an asymptote here. Wherever you stop that, you then approach this thing again as an asymptote. If you understand the picture of exponential curves, that begins to make sense. And we can take that all the way up to, I mentioned my grandson is graduated as electrical engineer. And he'll actually be working with power that comes out of nuclear reactors. Not with the nuclear reactors. We don't want him near a nuclear reactor. He's not trained. Not anywhere near the turbines because he's not a mechanical engineer. Just whatever comes out of that. And he doesn't care if it's coal, gas, nuclear, or whatever. It's going to be nuclear reactors for the most part. There are things that he doesn't completely understand about how alternating current works. And alternating current that comes out of every generator. And if you had a better understanding of this, you'd have a better understanding of how alternating current works. Okay. Now he can do the equations, he can do the math, but at the most basic level, there are things he could understand better. But in training as an engineer, you ignore those little details that any physicist would train for. Okay. And that's just the way the training goes. There's so much to learn that you kind of bypass the stuff that you're actually have an opportunity to understand better than most electrical engineers. But we're not going to make electrical engineers out of you this semester. unless you really want. I know how to teach electrical engineers the math and physics. Okay. As far as the engineering tricks they use, they leave that to the engineer. They don't interest me very much. Just like electrical engineers aren't all that interested in the finer details unless they're doing research. Okay. All kinds of things. Okay, well, I just mentioned all that because this picture of approach of an exponential function asymptote has implications that go way beyond anything you'll ever imagine. These are simple. Then you're not going to get into those, so I'm not going to give you the theory of complex variables and all that stuff. Yeah, you'd have to study for 7 or 8 years. Emphasizing that what you're going to learn from the assignments is going to be really important. Okay, it's going to be important to your field if you have a field that touches on any of the types of things I'm talking about: physiology, finance, engineering. Okay, just about any field. Like what happens to purchasing power when inflation goes up, inflation goes down. There it is. Okay. Like right now. Okay. I wasn't surprised everybody knew how to do 10% of 10,000, of 1,000. And I'm not surprised that the camera just decided to blur everything out. And it's still blurred out. Okay. Okay. So after 1 year, we have $1,100, right? Well, what we have is 1,000 plus 0.10 times 1,000, right? If that's 10% of 1,000, that's 100. So here's our 1,000. Here's our 0.10 times 1,000. Well, you can understand a little factoring. You understand that's 1,000 times 1.10. Okay. Now, I just added the need to. Well, okay, let me just do that in 2 steps. 1 plus 0.10 is 1,000 times 1 is 1,000. 1,000 times 0.10 is 0.10 times 1,000. Turns out to be 100. Okay. Okay, well, if you go for another year, you multiply that by 1.10. Because every time you add 10%, you're multiplying by 1.10. So after seven years, you're going to multiply by 1.10 7 times, right? we have 1.10 times 1,000 after 1 year, 1.10 times that after 2 years, 1.10 times that after 3 years. There's a pattern here. How many 1.10s am I going to have after 7 years? Show me with your fingers. You got enough fingers in your hand to show me? Yeah, I'm going to do that 7 times every year and multiply by 1.10. Well, that's 1.10 to the 7th times 1,000 years. So now I'm going to say P of T, which is your principal. If it's in a, that's what your investment's worth. Okay. It's 1,000 times 1.1 to the T. Okay. Terminology. That's the growth rate. Don't confuse that with a rate of change. It's a growth rate. A growth rate is not a rate of change. Okay. The 1.1 is a growth factor. So when you see thousand times 1.1 to the T, in this case, $1,000 would be your initial value. 1.1 would be growth factor, and the growth rate which we already know, 0.1 or 10%. Okay. So, important terminology. And you're going to see more about it with some explanation in your homework. On your homework, you immediately have problems of this nature. That use these ideas. Another example is RT is 12 times 1 minus 0.1 to the 2. What's the growth factor? Just have a minute to discuss this. I'll just pause for a second. Okay. Well, if you look here, how do we get the growth factor from the growth rate? We add the growth rate to the 1 to get the growth factor, right? So growth factor is 1 plus the growth rate. growth rate's negative 0.1. Meaning this thing's got a negative growth rate, meaning it's decreasing. So in this case, we have a positive growth rate, which means we have a positive exponential. Growth factor is greater than 1 over here. Growth factor less than 1 means a negative growth rate. It's a decreasing exponential. We flip across the y-axis. Now there's much more. You'll see it in the assignment. And email me if you have questions. Come by. I'll be around this afternoon. Get started on it early. And otherwise, have a good weekend. Very decent job on the major quiz. And look forward to seeing you do even better on the midterm.